Okay. There's one other thing in the chat. Let's see. Okay. Yeah, so we come to the examples. So we take the irrational rotation algebra, so the universal C-star algebra, which is generated by two unitaries u and v, subject to the relation du is e to the pi I theta uv, and theta is always an irrational real number here in this lecture. So we get the irrational rotation algebra. And we have an outer action of SL2Z on the irrational rotation algebra. And this is given a matrix N with the entries KL and M in SL2Z acts on a theta by the action. So if we just have to give the action on the generators. So it acts on U by e to the 2 pi I theta Kn. Kn is the first column, the first column of the matrix, UK Vn. And on V, it's just the second column which acts on it. So UE to the 2 pi I theta Lm, UL Vm. And SL2Z has exactly up to conjugation, exactly 4 finite cyclic subgroups up to conjugation. Of course, you can conjugate them around so you get more, but they act in the same way. So it's a Z2, which means Z mod 2Z, Z mod 3Z, Z mod 4Z, Z mod 6Z, and they are generated by those elements. So Z mod 2Z is generated by this, just by the minus the identity. The Z mod 3Z is generated by this, Z mod 4Z is generated by this, and Z mod 6Z is generated by this. So these are 6 finite cyclic subgroups. And there's a theorem which was proved in the case of Z mod 2Z by Bratelli and Kishimoto in '92. And in a paper by myself with Wolfgang Glück, Chris Phillips, and Samuel Walters in 2010, we looked at all the other cases. And we completely classified these fixed point algebras and the cross products of these finite groups acting on a theta. So we restricted the action of SL2Z to these finite groups. And one result was that the fixed point algebras and the cross products are always AF algebras. So these are all AF algebras, and they're very close, of course, to A theta itself, which is not an AF algebra. So the question is, are there choices F1, F2 in this list here, such that if I take the fixed point algebra Y1 and include it in the cross product by the other, is this C-star irreducible? And if this is so, then we get, of course, A theta as an intermediate algebra. So we have 2 AF algebras, A theta F1 and A theta cross F2, with A theta sitting in between. And we just have an example of 2 AF algebras, which with a C-star irreducible inclusion of 2 AF algebras, which have a non-AF intermediate algebra. And the answer by our theorem is this holds if and only if the intersection of these two groups is trivial. Because this is easy to see that this is equivalent to this condition C in the theorem. And so we get the following corollary. So if F1, F2 is any of the pairs in the list Z2, Z3, Z3, Z4, and here I say Z3 with Z3 tilde, and Z3 tilde is a conjugate of Z3. So I take, for instance, Z3 tilde is the group generated by this element. This is a conjugate of this element. So it also generates a group of. Then, of course, then it's easy to see that the intersections are trivial. And so the inclusion of A theta F1 into A theta cross F2, and also in the opposite direction, they are all C-star irreducible inclusions of AF algebras, and they all have A theta as a non-AF intermediate C-star algebra. And in the the case of Z2, Z3 is really the only case where we really fully understand the intermediate algebra. So the only proper intermediate algebras of this inclusion is a theta, and the other one is a theta Z2 cross Z3, which also sits, of course, inside. And this is also an AF algebra. So one intermediate algebra is AF algebra, and the other intermediate algebra is not an AF algebra in this case. But unfortunately, so far we lack a clear description of the intermediate algebras in the other situations. Also, we get sister irreducible inclusions if we take any element in SL2Z of infinite order, so we get an action of Z. And if we take any of one of the finite order, for instance, Z2, but also you can take any other finite subgroup, then this also gives an intermediate sister irreducible inclusion. And these algebras, they are also very well known. They have been completely classified by a paper of Böhnecke, Chakraborty, Suofeng He, and Chenchao Liao in 2018. So Böhnecke and Chakraborty, I wrote Chakraborty, I think wrong. They were PhD students of myself here and at the same time. And Suofeng he was a PhD student of Kawahigashi and spent 2 months in Münster as an intern during his PhD. And in this time, they came together and looked at this problem and gave very, very beautiful results. And interesting fact is, so if you have an element here in SL2Z, which has matrix trace equal to G, for instance, if you take this element, 1, 2, 1, 1, then the cross product of A theta by Z is again A theta. So in this case, you get a sister irreducible inclusion of these fixed point algebras into a version of A theta, which is not the old version. So, and which has actually A theta as a proper intermediate algebra. Yeah. So there are interesting things I think one can study here. So questions which are still open. So in general, is it possible to classify all intermediate algebras? So in the situation of our theorem, can we understand the intermediate algebras? As I said, we can do this in the case when H is abelian, and if the actions commute, then the inclusion of the fixed point algebra into the cross product is actually equivalent to this inclusion of the cross product by H into the cross product by H hat cross G. And then it follows from the Cameron-Smith theorem that the intermediate algebras are given by the subgroups of H hat cross G. And the case of Z2 and Z3, we could handle exactly with this result. But this is, of course, a very, very restrictive assumption. And there's one interesting example here. So if we take the irreducible inclusion of A theta Z3 into the cross product of A theta with this conjugate of Z3, then the only obvious intermediate algebra is A theta. And I would really think, I'm convinced that in this case, really A theta is the only intermediate C-star algebra of this inclusion of AF algebras. But yeah, so far we lack really the proof, and it would be very interesting to learn more about this question. Here are some papers. So I think it's yeah, we don't want to probably go into it. It's recorded, so everybody can go back to the recording and have a look at the references, I guess. And yeah, I would like to thank you for your attention and for your patience. And I really would like to apologize again for missing the right time. I'm very sorry about this. Thank you.
Thank you very much, Siegfried. Well, maybe if it's nice talk, I really liked it. If there is a little question, because I also have to go.
Yeah.
I actually have two questions. Maybe if I may. So the example of a non-AF algebra sandwiched between two AF algebras that you got is a theta. And of course, a theta is not AF, but a theta is a little bit close to AF because it's an AT algebra.
Yeah.
So the question would be in between two AF algebras, do you think that would you be able to prove the thing? Anything else is somehow approximated by finite objects?
I have no feeling for that. I have no idea. No idea.
The other question is, I mean, if you have a, I mean, the question is about transitivity of irreducible inclusions. So I guess it's clear that it's not transitive because of this requirement that they of alterness in your examples, right?
Exactly.
But
so for instance, I mean,
the question would it be possible to classify when is a double inclusion result giving you an irreducible inclusion?
So I mean, actually, I have to admit that I didn't think too much about this question because it's so obvious that in general you cannot have it. But it probably has to be a condition which somehow mimics outerness. So outerness of, so I mean, you see these conditions, for instance, this condition that A is that every element in B is full with relative to A. I mean, the condition ends up in some kind of condition which is a little bit has a little bit to do with this Kishimoto lemma, only a little bit, but it might be connected to that. So, for instance, you use the Kishimoto lemma to prove such a thing. I mean, and they are related in some sense. So, for instance, if you have a conditional expectation of finite index, there's a notion. People introduced the notion of outer conditional expectation. And so, for instance, our situation when we have finite fixed point algebras or finite cross products, I mean, you always have finite conditional expectations. Or in general, in our situation, we always had conditional expectations. So it might be also true that one can use this notion of outerness. And the outerness notion was a notion which is in one of the proofs. Maybe I can go back. In the proof of our main theorem, you see, we used that we can compress the difference between x and ex by some positive element with norm 1 to make it smaller than epsilon. And that was basically the definition of an outer conditional expectation by some people. I forgot the name, but I read this in Izumi's paper, for instance, that he mentions this. And probably one can see if you have two inclusions and both have conditional expectations, maybe that the composition of the conditional expectation has to be outer or something like this. But maybe then you get it for free for other reasons. But that sounds, for me, yet now it's really, I mean, just a thought I come up at this moment. But that could probably be something. Whether it's really worthwhile, I don't know.
Okay. Any other question? If not, I will stop recording. Oh, Alexander, maybe you have a question?
Yes, I just have a small comment. Like, hi Siegfried, thanks for
Hello, Alexander.
Nice to see you. Regarding the closure, I think you have to take them after all. I mean, so I wrote down like some notes, something like this.
Why?
Because for an abelian, for example, for an abelian C-star algebra A, you know that like the ideal is the same as the hereditary algebra generated by some element, and then like you have something commutative, yes. So for example, C01 half open, and if you take the identity function, then in the ideal is the square root, but the square root cannot be written as a, so the square root cannot be written as x times some vanishing function times x, like square root.
That's not unital algebra.
Yes, right, but I mean like, okay, so
of course I need
case,
unitality. The argument was that,
yes,
that the invertible elements are always open. And so if you have an ideal which has an element which is invertible, then also the closure. So if the closure has an element, then the ideal itself also has to have an element.
But what if you have just an approximation by like, I mean, like you have like, you always have an approximate unit in your algebraic ideal, but it's not clear if you have an ideal.
Yeah, but I think you are thinking still about the general case with the non-unitary case. I mean, it's really the simple fact that the invertible elements form an open subset.
Yeah,
so
perhaps is yes.
So and then you have a set that has non-trivial has trivial intersection if and only if the closure has trivial intersection. So
right. Yes, yes. Yeah, that's a nice argument also. Yeah, thanks.
Okay.
Okay, well, thank you again, Siegfried. I'm sorry, I will stop the recording.